If you've spent any time at all using an AI chatbot, Quinn, Claude, or, well, any of the big ones,
Oh, yeah, for sure.
then you've definitely seen one of the most curious patterns in computing today.
I know exactly what you're talking about.
You type in this massive, interesting prompt, you hit enter, and then
You wait.
you wait. There's this noticeable, maybe short, but it's a real delay.
Mm-hmm.
But then once that first word pops up, the rest of the response just streams out, token by token, at this really quick, steady pace.
That two-phase process, that's the tell. That's the sign that the infrastructure behind it is fighting this just huge mathematical battle.
It really is.
And that initial delay, what we call the prefill phase, happens because large language models are, at their core, just these incredibly complex next token predictors.
Right.
So for the model to generate even that first word, it has to process your entire prompt through billions of parameters. That's one single massive initial computation.
So for our deep dive today, our mission is to really unpack the mechanics of that, that expensive process.
And critically, to figure out how these services can possibly serve thousands of users at the same time, all running these huge computations without just, well, crashing or going bankrupt.
And the answer is this really clever optimization strategy.
It's called continuous batching. And it is specifically designed to maximize performance, to maximize the number of tokens you can generate per second, your throughput.
Okay, let's break this down then. We should probably start with the building blocks, which are tokens.
Right. You can think of them as sort of conceptual words or even pieces of words.
And inside the network, a lot of the initial operations are what we call token-wise.
Meaning the math for one token is totally independent of all the others, at least at first.
But if they were all independent, you'd just get word salad, right? A stream of nonsense.
Exactly. The magic moment, the point where tokens stop being independent and start to form meaning, where the word bat changes if it follows baseball or cave. That happens in one specific place.
The attention mechanism.
That is the single crucial layer where all the tokens interact and influence each other. It's what lets the model build a coherent thought across a long sentence.
And it's also where the computational cost just goes through the roof.
It explodes.
Okay, so this is where we get into the weeds, the technical deep dive. This is the bottleneck we're trying to solve.
It is. So let's imagine your input prompt is a sequence of, say, length no dollars. That prompt gets represented as a big array of numbers, a tensor, which we'll call $6.
And that tensor gets projected into 3 different roles.
3 crucial roles: the query, or 2, the key, or $8, and the value, or Valerie.
Okay, Q, K, and V.
The interaction, the part where the model measures the similarity between all the tokens, happens when you multiply the query tensor by the transpose of the key tensor.
Q, K, T dollar operation.
Right, and the computational cost for that single step is big O of n squared d.
That notation, $2, what does that actually mean for the user? I mean, what does it feel like?
It means the cost grows quadratically with the length of your prompt, $2. It's brutal.
So if my prompt is, say, 10 tokens long, it costs 100 units of compute time.
And if you double that prompt to 20 tokens, the cost doesn't double to 200.
It quadruples.
It quadruples to 400. If you make the prompt 10 times longer, the cost skyrockets by 100 times. It's a really, really nasty scaling problem that's just baked into the transformer architecture.
That perfectly explains why pasting a huge 10,000-word document as context can feel so sluggish at the start.
Precisely. The system is fighting that quadratic growth. And to manage this, we need something called the attention mask.
The mask.
Yeah, it's an essential tool. It's basically a matrix of true or false values that tells the model exactly which tokens are allowed to look at or influence other tokens.
Okay.
For language generation, we almost always use a causal mask. It enforces a simple rule. A token can only pay attention to the tokens that came before it.
So it can't cheat by looking ahead in the sentence.
Exactly. It has to predict the future, not read it. And this control mechanism is absolutely vital for everything that comes next.
And this whole process we've just laid out, taking the full prompt, fighting that quadratic cost, and finally calculating the scores for that very first new token, that is the prefill phase.
That's the bottleneck. That's the delay you feel.
Right. So once that first new token, let's call it token height plus I1, appears, we switch gears into the decoding phase.
Correct. The model's job is now to generate token $1 plus 2, 2. And if you design the system naively, It would just recompute everything.
For every single new word. It would do that whole dollar calculation
It
again.
would want to, yeah.
Mm.
It would recalculate the key and value projections for all the previous $1 plus dollar tokens every single time.
That would be computationally insane.
Yeah.
So how do we get around that?
Well, we take advantage of that causal mask. Since the new token we just generated doesn't change the attention calculations of the past tokens.
The past is the past.
The past is the past, so we don't need to recompute their key and value states.
We just save them.
We just save them. And this is the first critical optimization, the KV cache. We just store those computed $dollar states from the previous pass in a dedicated slice of high-speed memory.
And the benefit must be huge.
It's revolutionary. The KV cache takes the compute cost of generating the next token from quadratic $1 all the way down to linear dollars and dollars.
And that's why the rest of the words stream out so fast. We've escaped the recomputation trick.
You've escaped it.
Yeah.
But this performance gain comes with a big memory trade-off.
Let's put a number on that. How much memory are we actually talking about to store those K and D states?
It's not trivial. Let's take a model like Llama 2.7b. It has 32 layers, 32 attention heads, and a head dimension of 128.
Okay.
Just to store the K and V projections for a single token, that model needs over 8,000 values per layer.
Wow.
And if we use standard float 16 precision, that adds up to 16 kilobytes of memory to store the KV cache for just one token.
Hold on, 16 kilobytes for one token.
Yep.
So if I paste in, let's say, a 10,000 token document as context, like a decent-sized PDF, the system needs 160 megabytes of super-fast GPU memory just for the cache before it even generates the first new word.
That is the exact constraint.
Is that even sustainable? I mean, a GPU only has so much VRAM.
It's a huge burden on memory. The cache is a blessing for speed, but a curse for memory.
Yep.
And it becomes a critical problem when the initial prompt itself is massive.
So if the prompt is too long for the GPU to hold all at once, the whole system just crashes.
It used to, but not anymore, thanks to another piece of the puzzle, chunked prefill.
Chunked prefill.
Yeah. So let's say you have a prompt that needs 7 tokens worth of computation, but your GPU can only handle the memory for 4 tokens at a time.
You just split it.
You split the prefill into chunks. You process the first 4 tokens, you use the KV cache to store their K and V states, and then you process the remaining 3 tokens.
And in that second pass, I'm guessing you somehow use the cache from the first chunk.
You prepend it. The system takes the stored KV states from the first chunk and just sticks them onto the front of the new ones being computed.
I see. So the KV cache isn't just for getting from prefill to decoding. It also lets the prefill itself be broken into pieces.
Exactly. Chunked prefill lets the model handle these impossibly long initial inputs by breaking the work down into manageable steps that fit within the GPU's hard memory limits.
Okay, so we've pretty much optimized the single user experience. We have chunking for huge prefills and the KV cache for fast decoding.
Right. But the real goal, the commercial goal, isn't serving one user perfectly. It's about serving thousands of users at once. It's about maximizing throughput.
Which brings us to batch generation. The obvious solution is just to grab, say, 8 or 16 prompts and stuff them into a batch. Process them all in parallel.
And that's how it started. And that's also where the whole system just breaks down catastrophically.
Why?
The fatal flaw is that computer memory needs tensors to be rectangular. So if you have 8 prompts in a batch and the longest one is 100 tokens,
Oh, the other 7 have to be padded. You have to add filler tokens to make them all 100 tokens long.
and you waste so much compute processing useless padding tokens that add 0 value to the output.
And the waste gets even worse during decoding, right? Because if one prompt in that batch finishes early, it generates its end-of-sequence token.
But the system has to keep going. It's forced to keep generating useless garbage for that finished sequence until the absolute slowest, longest prompt in the batch is done.
That's just utilization suicide.
It is. So, of course, engineers tried to fix this with dynamic scheduling. The moment a request finishes, you swap in a new one immediately.
Which sounds smart. Keep the GPU busy.
It sounds smart, but in that rigid, rectangular batch setup, it makes the padding problem explode.
Explain the explosion.
Okay, let's use your example, a batch size of 8. 7 of those requests are already happily decoding, generating just 1 token each. Then a new user submits a huge 100-token prompt that needs prefill.
Oh no. To keep that tensor rectangular, those 7 single-token requests now have to be padded all the way up to 100.
Correct. For that single forward pass, you now need 99 padding tokens for each of the 7 other requests. That's 99 times 7, which is 693 useless padding tokens.
693 wasted computations in one cycle.
Wasted computations that the GPU is forced to calculate.
That is utterly ridiculous.
Yeah.
It's so inefficient. It proves that the batch axis itself, that rigid shape, is the core of the problem.
It is the problem, and the only way out is this radical idea. Just get rid of the batch axis completely.
So you don't care about the number of separate sequences anymore.
You only care about the total number of tokens you can fit onto the GPU, period.
This is where we get to the secret sauce of continuous batching. This is ragged batching.
Exactly. Instead of separate padded sequences, we just concatenate all the active prompts, whether they're in a long prefill or quick decoding step, into one giant continuous sequence.
It's ragged because the original sequence lengths are all uneven, and we just don't care about padding anymore.
The only limit is the total available memory for tokens, not the length of the longest prompt.
But how do you stop user A's tokens from interfering with user B's tokens if they're all in one big line?
You go back to our fundamental control tool, the attention mask. We just adapt the mask to create invisible walls, strictly forbidding tokens from user A's request to ever interact with tokens from user B's request.
That is just brilliant design. The attention mask started as a tool for causality, but now it's being repurposed as a traffic cop for concurrent users, all without a single padding token.
And that, when you put it all together, is continuous batching. It's the integrated strategy that powers basically every efficient modern LLM service today.
So let's recap the three components that make this work in harmony.
Go for it.
First, you have ragged batching, which kills the padding waste by just concatenating everything together and using the attention mask for isolation.
Second, you layer dynamic scheduling on top of that. The moment a prompt is done, it's out, and a new request is in. The GPU stays at 100% utilization.
And third, you use the flexibility of chunked prefill and the KV caching to fill any leftover memory space with parts of long new prompts.
Which lets you seamlessly mix those huge, slow prefill calculations and the rapid single-token decoding steps in the very same forward pass.
So this whole thing moves LLM serving from a static, inefficient system that's always waiting on the slowest user
to a truly dynamic one. It uses every single available compute cycle, which is how these services handle all that concurrent traffic and achieve these mind-boggling levels of throughput.
It's amazing. This whole deep dive started with that simple observation, the wait, then the stream.
And now we see it represents this titanic engineering effort to battle quadratic complexity and padding waste.
And continuous batching is the solution.
Absolutely. It's the infrastructure that makes LLMs commercially viable at a massive scale.
Now, we did note that continuous batching is all about maximizing throughput by using the GPU's compute cycles perfectly. But that memory cost of the KV cache, that 16 kilobytes per token, is still a huge liability.
It is, especially as context windows just keep getting bigger and bigger.
The sources suggest the next step in this evolution is a complementary technique. It's called paged attention. So, if continuous batching solves the compute scheduling problem, paged attention is all about optimizing the memory management of that massive KV cache. So here's a thought for you to take away. What further efficiencies do you think managing that memory like a virtual memory operating system could unlock for the future scale of LLMs?